paper usually belongs to a major research
exist
in which we are so
Hello.
Hello everyone, my name is Felipe Lopes from the Federal University of Paraíba, and I'm here today to present the paper A Deeper Look at Source of Errors that Affect the Classical Double-Ended Travel Wave-Based Fault Location Method. This paper was written in partnership with colleagues from the University of Brasília, from the Federal University of Paraíba, from CEPEL and from EVOS. The double-ended travel wave-based fault location method has been increasingly used in real systems, and the promising performance has been verified. As a consequence, the interest from utilities has increased, and it is motivating several studies on travel wave-based fault location applications, especially using the double-ended approach. However, we found that the literature is still scarce of sensitivity parametric studies, such that the goal of this paper is to present a sensitivity parametric analysis on source of errors that affect the double-ended travel wave-based fault location method, but explaining how source of errors interact between themselves and with system parameters. To apply the classical double-ended travel wave fault location formula, it is necessary to detect the arrival times of the first incident travel waves that are launched from the fault and that reach both line ends. These arrival times are represented here by the timestamps TR and TL, and these timestamps can be used to calculate the time period delta TRL, which can be associated with settings of the line propagation velocity and line length in order to calculate the fault distance D from a given reference terminal. However, in practical applications, we know that line length can vary depending on the weather and line loading conditions, so that we are considering here an uncertainty factor called delta L. In addition, travel wave detections at both line ends may present deviations, which are called here delta TL and delta TR. Also, regarding these timestamps, we know that time synchronization errors may take place because we are associating remote and local timestamps. So this time synchronization error is represented here by the variable xi. And combining xi, delta TL and delta TR, we can calculate an equivalent time period error P, which is given by this formula here. Finally, regarding the propagation velocity, we know that it depends on the line parameters, and the line parameters can vary according to weather and line operating conditions. So we are also considering a variable that represents errors in the VP settings, and this uncertainty factor is called here delta V. So including all these uncertainty factors into the fault location formula, one can obtain this extended formulation in which the first term represents the correct fault distance estimation and the second one represents the error term. Regarding such an error term, from a mathematical perspective, we can analyze it by means of sensitivity factors which can be calculated in relation to different parameters. Here we are considering beta parameter which can represent delta L, delta V, P, delta TR, L, and VP. It is important to emphasize that in red color we are representing the uncertainty factors, which are actually errors that can take place when the fault location procedure is applied. But in blue color we are highlighting parameters which are not errors, but they are they are parameters which depend on the fault position, like this time period here, and or which depend on the system parameters like the propagation velocity. So these sensitivity factors can be calculated in order to explain how these errors will behave when these parameters vary. Before conducting this study, a reference case had to be defined. And to do so, we considered a transmission line with length equal to 100 kilometers and with propagation velocity equal to 98% of the speed of light. Aiming to obtain a more realistic reference case, we considered some slight errors here in delta L, delta V, and P. And these errors, when we varied the fault distance with steps of 5 kilometers over the simulated transmission line, we could obtain such an error curve, which has a characteristic which is very typical for double-ended traveling wave-based fault location methods. And we have seen this type of curve, which we're calling here as V-curve with a central band here. This type of curve is very reported in the literature when this type of matter is analyzed. So we used this reference case, and different parameters were varied, providing different combinations in order to evaluate how the source of errors interact between themselves and with the system parameters. Initially analyzing the influence of delta L, we can see that delta L does not interact with any other variable here in the numerator. The denominator is the same for all these sensitivity factors, so we are focusing mainly on the numerator of these expressions. And as a result of this particular effect, we can see that the error surface, it rotates toward the delta L plane, leading the band of the V-curve to rotate as well. On the other hand, when we analyze the delta V variable here and we consider the error sensitivity to delta V, we can see that delta V interacts with the time period delta TRL, which is in turn a function of the fault distance. So when the fault takes place close to the middle of the line, delta TRL assumes values very close to 0, canceling the effects of delta V, which can be observed here in this result because the V curve can be observed for all evaluated values of delta V with no rotation here. On the other hand, analyzing such the 30 expression here, we can see that P interacts with VP, but here we are varying P against T, so there is some interaction between P and VP. P leads the V curve to rotate. We can see that here there are regions as well in which the fault location error is very small, but when P increases, this band disappears, and so it dictates the errors which assume values in the order of 3 kilometers, for instance. Going deeper into this question, we decided to evaluate the interaction between P and V by varying VP, which is this variable which depends on the system characteristics. And we can see that considering two different velocities, increasing the velocity, a rotation occurs on the error surface. It indicates that VP also interacts with P, changing the error behavior when the fault distance varies. So it is an interesting finding that shows how these variables can interact and how they can be difficult to predict in practical application. And finally, evaluating now the relations between P and delta V, we opted to demonstrate here two cases in which we have a closing fault and then a fault close to the middle of the line, just to demonstrate that delta V and P, they interact between themselves, but the fault position which dictates the value of delta TRL, it also enters in this interaction, it also interferes in this interaction, so it changes the behavior of the errors, making these surfaces to rotate. So delta TRL changed the interaction between P and delta V. This is the conclusion from these results. So as the final conclusions, we can say that the proposed sensitivity analysis provided a comprehensive understanding about the influence of source of errors that affect the double-ended traveling wave-based fault location method. The calculated sensitivity factors revealed mathematical relations between source of errors, indicating that some of them modulate others and some source of errors can be affected, can be interfered by the system characteristics. So depending on the combinations, errors can aggravate or they can reduce, and depends on the combination between these variables from the errors in the settings of the method and also in relation considering different values on the system characteristics, for instance in propagation velocity and line length. From a practical perspective, we could conclude that using universal settings in propagation velocity is not recommended because it increases the chance of higher values in delta V, and delta V interacts with most of the evaluated variables, which is a good point to see in practical applications because it can lead to huge errors. It is also recommended to avoid travel wave detectors which result in different errors at both line ends because it will increase the equivalent P error and it can be superposed with time synchronization errors, and this is why we are recommending here to consider reliable time synchronization means to minimize these errors, because the equivalent P error also interacts with errors in the propagation velocity and other variables analyzed in this paper. And finally, we could see that depending on the combination, even when we consider errors in the settings and in the detections, there are some regions which present small errors. It depends on the combination. So obtaining small errors in a given case does not mean that the travel wave method using the double-ended approach is properly configured. So we recommend to take care about these questions and to do not believe that your algorithm is properly configured if you have a good result in a particular case. So this is our paper and we thank your attention. Thank you.
This paper usually belongs to a major research system, which we are still.
Hello.